You've heard black holes described as cosmic vacuum cleaners, sucking in everything nearby. That's wrong. Swap our sun for a black hole, and Earth wouldn't get pulled in at all. We'd just keep orbiting and slowly freeze to death. What actually kills you depends on which black hole finds you, and for some of them, physicists still don't agree on how the ending works. Fall toward a stellar mass black hole, the crushed core of a dead star, and physics kills you long before you arrive. At the event horizon of a black hole 10 times the sun's mass, the tidal acceleration between your head and your feet hits roughly 19.6 billion meters per second squared. For comparison, standing on Earth, gravity pulls on you at about 9.8 meters per second squared. Your body stops being a body about 700 kilometers out. That's not a rough guess. That's the calculated safe distance, the point past which no human tissue survives intact. Every stellar mass black hole in the galaxy, and there are tens of millions of them scattered across the Milky Way alone, kills the exact same brutal way, violently, and well before you ever cross a horizon. Now try a bigger one, and the ending gets genuinely uncertain. Cross into a supermassive black hole like S50014 plus 81, 40 billion times the mass of the Sun and 236 trillion kilometers across, 47 times the distance from the Sun to Pluto, and the tidal forces at the horizon are gentle enough that you could survive well inside it. From outside, onlookers would watch you slow down, redden, and fade at the horizon, frozen there forever as far as they are concerned, while you would watch their entire universe race past in fast forward. But what happens to you next is where physicists split into two camps. One theory says space itself curves so sharply past the horizon that only one direction exists anymore, like a tight alley closing behind every step, and you eventually stretch into a stream of plasma 1 atom wide. The other says you would hit an invisible wall of radiation called a firewall and be terminated instantly, no stretching at all. Same black hole. Two completely different deaths, and nobody currently knows which one is real. Some black holes never let you get close enough to cross anything at all. A star that wanders too near a supermassive black hole gets shredded from a distance in what astronomers call a tidal disruption event. Roughly half the star's mass stays gravitationally bound, forms a glowing accretion disk, and lights up the sky for months as it's consumed, bright enough that telescopes on Earth catch these flares happening in distant galaxies every year. The rest is flung outward into space at enormous speed. Sometimes the star only loses its outer layers and survives as a stripped, wounded core, doomed to swing back and be shredded again on its next pass, sometimes years later. That star doesn't die once. It dies in installments, over and over, sometimes for years, until nothing is left to strip and the flares finally stop coming back. Here's the death nobody expects. A primordial black hole small enough to fit inside an atom needs no gravity at all to kill you. Physicist Robert Scherer calculated it in 2025. A black hole of about 140 billion metric tons, 7 times the mass of the asteroid Tutatis, but barely 0.4 picometers wide, smaller than a hydrogen atom, moving at roughly 200 kilometers per second, wouldn't stretch you or spaghettify anything. It would punch a supersonic shockwave straight through your tissue, the same wound profile as a .22 caliber bullet. Only at nearly 50 times that mass would tidal forces alone be strong enough to tear apart brain tissue on their own. Gravity isn't the weapon here. Speed is. A quasar does not even need to touch you to end you. Feed enough gas into a supermassive black hole and its accretion disk can outshine every star in its entire host galaxy, roughly 100 billion stars combined from a region smaller than our solar system. That light alone, no jets required, strips atmospheres off planets light years away, boiling gas particles until they escape the planet's gravity for good. Researchers calculated that if the black hole at the center of our own galaxy flared to full brightness the way active quasars do, unprotected complex life within 8 to 13,000 parsecs would take a lethal radiation dose. You would not need to fall in, you would just need to be in the same galaxy on the wrong side of the light. Point that same light directly at Earth and it becomes something worse, a blazar. It is the identical quasar, just aimed straight down its relativistic jet toward you instead of sideways, and relativistic beaming boosts its apparent brightness until it outshines nearly everything else in the observable sky, flickering wildly within hours as the jet's inner engine shifts. Wrong place, wrong angle, and death is not gradual erosion anymore. It is a targeted beam of gamma rays crossing the galaxy, and the only thing that decided your fate was geometry, not proximity. You could live safely 1,000 light years from a black hole for 1 billion years and still die the moment its jet happens to swing across your address. Some black holes skip you entirely and kill their neighbors instead. Cygnus X1 is a 21 solar mass black hole locked in a 5.5-day orbit with a supergiant companion star 41 times heavier than our Sun. For millions of years, it has been pulling the star's outer atmosphere away, strand by strand, heating that stolen gas to millions of degrees as it spirals inward and screams out as X-rays bright enough to be one of the strongest sources in our sky. The companion isn't crushed in an instant. It's eaten alive, in slow motion, in full view of every telescope pointed at it, losing itself one stripped layer at a time. Eventually, if it loses enough mass, the dying star's own core could collapse too, feeding the black hole one last time on its way out. Then there's the singularity itself, the one place where every rule listed so far stops applying. Inside a naked singularity, general relativity predicts infinite density with no event horizon hiding it from view, a theoretical object where the equations simply break down and stop predicting anything at all. Most physicists suspect nature always hides these behind a horizon, a rule nicknamed cosmic censorship, precisely because a naked singularity makes cause and effect stop making sense. Nobody can even tell you what dying there would look like, because the equations that describe every other death on this list simply stop working at that point. And here's the final twist. Black holes die too through Hawking radiation, and the smaller they get, the more dramatic the ending. Shrink to the mass of a large asteroid and a black hole radiates at roughly room temperature. Shrink to the mass of a mountain and it glows with about the heat of our sun. In its very last second, it releases the energy of billions of nuclear bombs in a single flash. The catch is the timescale. The biggest black holes we know of could take up to a googol years to fully evaporate, so long that the universe will have gone dark and uninhabitable long before any of them actually finish dying.